the electrostatic analog. Now it is the analogy or similarities between that is the electrostatic field or the electric field and the magnetic field. So we are going to establish some relationship. We are just going to compare the equations what we had derived in chapter 1 and chapter 2 for electrostatics, how far they are related to the magnetic fields which we have studied in the last chapter. The first thing, we were describing the electric field by an E vector, the magnetic field is described by a B vector. That is the first thing. Then the constant there in the electric field it was 1 by 4 pi epsilon naught. In the magnetic field the constant is mu naught by 4 pi. Then the next thing is the equivalent, that is the field equivalent, that is the magnetic field on the axis, axial field. This was E equals 1 by 4 pi epsilon naught. It was 2p divided by r cube. This was on the axis. Similarly, for the magnetic field, it was b axis. It was mu naught by 4 pi 2m divided by r cube. So this was the axial field for the electric dipole. This is the axial field for the magnetic dipole. Now, similarly, equatorial field. E equatorial was equal to minus p divided by 4 pi epsilon naught r cube. The magnetic equivalent is, again, it is going to be minus mu naught divided by 4 pi r square, r cube, that is going to be. So this is the equivalent field in terms of, this is for the electrostatic part, this is for the magnetism part. Then one more thing was the dipole moment. Here the dipole moment was P is equal to Q into 2A. Here it is going to be in terms of, there will be two equations. Here is going to be M is equal to I into A, that is when we are using a solenoid or a loop, that is the current carrying loop. And if we have a bar magnet, the same M is going to be given by Qm into 2L. 2A represents the length of the dipole, 2L represents the length of the magnet. If it is a circular current loop or if it is a revolving electron, then the dipole moment will be calculated as M is equal to I into A. So the torque produced, so here it was P cross E, because all three are vector. Here it is going to be tau is equal to M cross B. Again, all are vectors, and the torque is going to be in a perpendicular direction to the plane containing P and E. Similarly, in this case, it will be M and B. The other thing which we had derived in chapter 2 for the electric field was the potential energy. So potential energy U was equal to, it was P dot E. So it will be PE cos theta, and similarly this U will be equal to M dot B. Things will be same for these two, that is the torque and the potential energy of the dipole will be same. The only difference is here it is a cross product and here it will be a dot product. It is again based on similarity because almost all the things are similar. E replaced by B, 1 by 4 pi epsilon naught, 1 by 4 pi is found here, epsilon naught comes in denominator, mu naught is in the numerator, there is the only difference. Then E axial, again same, 2 times of dipole moment, 2 times of dipole moment, it is proportional to R cube, this is also inversely proportional to R cube. Same thing for the equatorial field, it is a negative sign, here also we are getting a negative sign, here also it is inversely proportional to R cube, both cases are same. The dipole moment, because the magnet or the magnetism can be implemented using two things. One is by using a directly a bar magnet, or we can use an electric dipole, there is a current carrying loop. In that case, we are going to have two different equations for the dipole moment. Then it was the torque, that is P cross E, same thing in magnetism is going to become M cross B. Then finally, the potential energy, it is P dot E, here it is going to be M dot B. For the torque, it will be a sin theta, for the potential energy, it will be a cosine theta. And as we have derived for this one, it will be rather cos of theta 1 minus cos of theta 2. Similarly, we are going to have that cos of theta 1 minus cos of theta 2 for this one. So by what angle or from what initial angle we are moving that dipole or the magnetic needle from one position to another position. So it will be theta 1, theta 2, two different angles we need. The same thing applies for the electric dipole, the same thing will be applicable for the magnetic dipole.